Good evening, all. So, welcome to the week 12 problem solving session for the course Matlab Programming for Numerical Computation. So, this is our last week of the course. So, basically, what we'll be trying to cover this week is a recap, maybe a short recap of like what all we discussed this entire course. And we'll also try to solve some problems that combines different theories that we learned throughout the course. So, I'll be first going through what we learned in the recorded lectures, and then we'll try to solve some problems. So let me begin the session. Okay, it's just 6. So let's wait for like 2 more minutes to see if there are more people to join, and we'll start the session by 6 2. Okay. So whoever is there in the meeting, please do stay. So let's begin today's session. So first we'll be looking at the things that we tried to learn or understand during this course was first we went through the basic structures of MATLAB code. So in basic structures of MATLAB code, first what did we do? Just a second, let me just annotate. Okay. So first in basic structure of MATLAB, we learned that we start with, if you're starting with a function, you have a function definition line. Okay. So in this, there are two aims. One is to pass on variables, that is inputs. Then we had outputs. And then we had a set of statements. And then we had the end. Okay. So this were like the basic MATLAB structure for a function. For a script also, this is what we follow. First, we initialize the variables. Okay. Then we perform certain tasks. And then we display or print them. So how to take the inputs, how to do arithmetic operations, and how to do the print and display statement, all this we have already seen. So that was about the basic structure of MATLAB. Now arrays and matrices. So this is also very, very important feature of MATLAB, that how easy it is to handle arrays and matrices using MATLAB makes our life so much easier. So here in arrays basically we had like the one dimension. So array is like one dimensional. It could be either row or it could be column. And then we saw the colon operator. Okay. Then coming to matrices, we talked about matrix generators. What are they? Like ones, zeros, etc. Then we talked about how matrix indexing work and how to extract a certain part of a matrix using indexing. How to make matrices like concatenating and stuff like that. Okay. And then we also saw matrix operations. That is addition, subtraction, multiplication. and element-wise operation. So you remember the difference between star and dot star, okay? The element-wise multiplication and all those things. So this matrices can be used at several places. The ideas that we learned using this matrices can be extended to several practical problems also. Now the next is MATLAB functions and MATLAB scripts. So functions, scripts, we try to understand what is the basic difference between them. This takes inputs and gives outputs. It is used when for a specific task. It's used for a specific task, like maybe to find the sum of a number, to find the to actually take input of the marks of all the students in the class, then try to find the average and all those things. Okay, so it's for a specific task. Then what happens? We also said that the variables in a function are local to the function. So these variables don't have access outside the function. Okay. When scripts, what happens? In script, it doesn't take inputs, outputs, but you can always initialize certain variables. And this is when we have a set of commands to be saved and which can be used in the future. This has a set of commands. Now what happens? The variables that we use here are global and it can be seen in the workspace. Okay, this is in the global workspace. You will be seeing it in the Matlab workspace. However, in this, the workspace is only specific to the function workspace. Okay, so these were the things that we saw difference about the functions and scripts. Next is we also saw about writing, coding, and debugging. That as we progressed, we understood that the MATLAB will give you flags when you have a mistake in your code and how to debug those, all those things we have learned through practice. Next important thing is what kind of problems did we see? So this is just a broad classification of the problems that we saw here. One is linear equations and nonlinear equations. Basically, if you have a system, f of x is equal to 0, how to solve them? Okay. So in linear equations, what happened? Every linear system can be written like this. Ax is equal to b, where A is a coefficient matrix. You have a x, which is a column matrix, and b, which is a constant matrix. Okay. So this is A, x, and b. And then what happens? X can be always calculated as A inverse of B. So this A backslash B is same as calculating inverse of A multiplied by B. Then you will be getting, if it is having x1, x2, x3, this will give you the answer of all the x1, x2, and x3. Here also, if you remember, we had seen to check if the system has unique solution, if the system has infinitely number of solutions, or the system has no solutions. Such systems also we have seen and how to differentiate them in a linear system. Now we saw something also non-linear system. Okay, non-linear system we saw there are iterative methods for finding non-linear solutions. But apart from that, we also saw inbuilt MATLAB routines such as F0 and FSOLVE. Now the next category of problems that we saw was differentiation and integral integration problems. In differentiation, what we saw central differencing, forward differencing, backward differencing. We saw how the errors works and how the errors propagate. We also saw how the truncation error, all those things, machine precision and all those terms was discussed when we were doing the differentiation. Now integration, we have the trapezoid rule Simpson's one-third rule, and we also saw the inbuilt MATLAB command of traps. Okay, and you have such integration and differentiation routines that are available in MATLAB. Next is curve fitting category. In curve fitting, there were two things. One is regression and interpolation. Regression is basically you're trying to find out there is a function which satisfies all your x values. So it will be in the form of f of is equal to 0. Try to find this function. That's what we did for regression to find the model. Okay, so this was what was done by regression. But on interpolation, what we did, so interpolation, if I have a value at x1 here, I have a value at x3 here, there is some point x2 here. Okay, given these 2 points, I need to find what will be the value of some point that is falling between these two. So that is interpolating between your data. Okay, so this is what we try to do using interpolation. Then a different class of problems, it was a wide category of problems that we discussed, which was differential equations. In that we had ordinary differential equation and partial differential equation. Ordinary differential equation means it will be like dy by dt. There is only one independent variable. Okay. And in this dy by dt, if you are given an initial condition, that is at t equal to 0, your y was something 1. If the initial condition of the system is given, then it is an initial value problem. If the boundary values are given, that is at t equal to 0, y value was 1, and at t equal to 10, the y value was 2. So the two boundary conditions are given, then it falls under the category ODE BVP, boundary value problems. Okay. Now coming into partial differential equation, what was it? Partial differential equation will have dou y by dou t or something like dou y by dou x. So here there are two independent variables. Both x and y are independent variables. Okay. So these are the things. So next is we have differential algebraic equation, which is a bonus thing, bonus chapter that was taught to you. We'll not be discussing that and we'll not be having that for the exam. Now we'll talk about how to combine these multiple techniques that we learned in a single problem. When you find a problem, how do we use this multiple knowledge about this multiple kind of techniques that we have to try to solve a problem? So that is, first we'll look at the methods that we have already seen. Okay, you may not have realized, or some of you might have realized that we are actually combining different techniques that we learned. So the first is the shooting method. So shooting method, if you observe, we did it for calculating the double derivative. So just give me a second. Yeah. So how do you solve such double derivatives? That is, if we have d square t by dx square, first we'll define a new variable. So let my variable be y. Okay, we'll declare that y is equal to dt by dx, and then we differentiate it again. That is dy by dz is equal to d square t by dz square. So that becomes automatically gamma t minus 25. Now we declare a capital Y in such a way that the first variable comes from here, that is t, and the second variable comes from here, that is small y. Okay, so now the whole system can be classified into two first order ODEs. Okay, and finally, how will it look like? So first we'll have a system like d by dz t comma y, and this will be equal to y gamma t minus 25. Okay, and how do you solve this? If you are given boundary conditions, so here the boundary conditions is t at z equal to 0. So the whole thing is if you have a road, okay, with z, so this is z equal to 0 and this is z equal to 1, you discretize into several points. Okay, so discretize that into several intervals. And here at this, the t is equal to 100, and at this, the t is equal to 25. Okay, if that is the case, we need to find what is the t value at each of these intervals. Okay, so this is a boundary value problem. So what we can do is this boundary value problem can be converted into an initial value problem, and such initial value problems can be easily solved using your ODE solvers that you have. Okay, so first let us try to do that. Now what you'll do is we have given two conditions. That is, the only t is given to you, but your capital Y is basically d by dz of t comma y. This you don't have any knowledge of y here. So what do we do? So let us assume. So initially what we do is we let us guess the value. We let us guess value for y. Okay. Then what happens is, so we'll get the value for y. So what will happen? We'll have the t. So we'll guess the value for y at z equal to 0. At z equal to 0. So at z equal to 0, you will have both t and y, and this whole thing can be solved as an ordinary IVP problem, ordinary differential equation IVP problem using your ODE solvers. Okay, so this is what I call it as y at 0. Now we were using also using the ODE IVP problem, we find the solution. But in the solution, what will happen? You will have a temperature that is given at the end of the road. At Z equal to 1, ODE will give you a temperature. Okay. And this temperature has to be exactly matching to this value that is given to you in the question. If that is not matching, you calculate the residual. Residual is a difference between this and this. Okay. So what we do is we initially take a guess of y at z equal to 0 in such a way that the residual, for one reading it is positive, in the other reading, another guess. Okay, this is y guess 1 and this is y guess 2. So this you assume that the residual is negative. Okay, now what you do, you take a midpoint of this. So that is the bisection rule. And then we calculate at the midpoint of that guess, let it be G3 guess. Okay, at y G3, we again check the residual. Based on its sign, whether it is positive or negative, we'll discard any one of it. And you'll keep reducing the bracket just like you do it in the bisection method. So how many things did we see here? So here what happened is we are solving ODE BVP to ODE IVP. Okay, we are using bisection method to solve a nonlinear equation. Here in this case, this is a linear equation, but there could be nonlinear equations also. Okay, so here we have used a lot of things, lot of methods combined. So now what happens is instead of bisection rule, you could also use Newton-Raphson if you want to get the new point G3. And you keep repeating the step until your residual is equal to 0. That is, after solving the ODE IVP, the temperature at Z equal to 1 should be equal to 25. This is the condition that you check. Okay, any questions? So these are the methods that we combined in the shooting method. Okay, the next is the method of lines. In the method of lines, what are the things that we try to combine? One is differentiation, the other is the ODE IVP problem. Just like we used to do before. So here what happens is in method of lines, it is a transient case. So that is, it has a dou by dou t term. That is, the system is changing with respect to time also. In that case, what do you do? So in that case, you can simplify this using central differencing or backward differencing. Okay, then what happens? Then you will get a system of equations which are like this. Dou t by t, you will have a equation. Let me assume it to be f of temperature and time. Okay, so now this becomes an ODE problem. Not an ODE problem, which is in one variable. That is t. Only time is your variable. Okay. So here what we use is we use central differencing or upward differencing formula for each term, convert the whole thing into a set of ODEs, and using that set of ODE, we solve the set of ODEs using your ODE IVP solvers such as ODE 45, ODE 23S, ODE 15S, and so on. So let's look into that. So here if you have your double derivative term, this is the central differencing formula for the double derivative. T at a double derivative at a grid point I is equal to Ti plus 1 minus 2Ti plus Ti minus 1 divided by delta x square. Okay, this is your central differencing term. So let's put this back into the equation. So at the first grid point, that at the ith point, dti by dt is equal to alpha, the central differencing formula, minus beta, Ti minus Ta. Likewise, when you write the equation, for you, the T1 is given to you, that is 100, Tn plus 1. That is, if you are n intervals, we will have n plus 1 data points. Okay? Out of the n plus 1 data point, first and the n plus 1 is known to you. So this is 100 and this is 25. So you have to find from 2 to n. So this equation, you write it from d T2 to dTn. Okay. So now this T2, T3 till Tn, you call it as the vector you're trying.
Is this clear? Any queries?
No, ma'am.
Yeah. Just a second. Just give me some time. My earphones got disconnected, but I think I'm still audible. In case I'm not audible, please do let me know in the chat box. Okay. So this is how we solved using the method of lines. And then what happened is we had a set of equations. Like you have an equation for T2 to Tn. And this you will be trying to solve using the ODE solver ODE 45. So this was using the method of lines method. Next is method of lines for hyperbolic PDEs. So here also we have a transient term that is changing with respect to time, and this is a term which is changing with respect to position. So what do? The trick that we used before, that is with respect to position we apply either central differencing or backward differencing, and we convert into a set of ODEs. Okay, and then we try to solve the set of ODE using some ODE solver such as ODE 45. So here what happens is, here we have a dou theta by dou t plus u dou theta by dou z is equal to minus k theta. At time t equal to 0, we have the theta value to be 0, and at z equal to 0, the theta value is equal to 1. This is an analytical solution that is for the steady state. Steady state means what will happen? We are assuming that this is equal to 0. With respect to time, the system is not changing. Then what will happen is dou theta by dou z is equal to minus ku by theta, and the solution, if you integrate it back, this will be an analytical solution for steady state. That is very important. Okay, this is only for steady state. So using method of lines, what will happen is, just like we did earlier, we have an Z road is there, which we divide that into particular intervals from 1 to n plus 1. N intervals, each the difference between two intervals will be L by n, given L is the total length of the road. And then what will happen? We discretize, convert into n ODEs and solve it using the ODE solvers. We'll quickly go do a recap of how it's been done. So this is using the central differencing formula. Remember that in this question, we have only given the information about the first grid point. Okay. 2 to n plus 1, we have to find out. In the earlier case, we had the 1 and n plus 1. So in that case, we have to only solve for 2 to n. Here you only have 1, so you have to calculate for 2 to n plus 1. So in this, for this, if you are using central differencing formula, that is the theta I plus 1 minus theta I minus 1 divided by 2h, put that back into the equation, you will be getting an ODE. That is from theta 1 to, sorry, theta 1, theta 2 up to theta n plus 1. In this is already known to you. So this is the unknown or unknown quantity that you're trying to solve for. Okay, but there is a problem. At this point, at theta n plus 1, if you are using the central differencing, you will require theta n, sorry, let me just do it. So if you are calculating for the grid point I is equal to n plus 1, then your central differencing formula will be like theta n minus theta n plus 2 minus theta n divided by 2h. We don't have this quantity. So what will happen is, in central differencing, if you are using from 2 to n, use central differencing, and for the n plus 1, we use the backward differencing. Okay, so this is what you do if you are trying to solve using central differencing formula. Otherwise, one other option is, for all the points, that is from 2 to n plus 1 points, let's do the backward differencing. So the backward differencing is I minus theta I minus theta I minus 1 divided by h. So if you are trying to do it for the last point, that is when I is equal to n plus 1, your dou theta by dou t at n plus 1 will be equal to minus u theta n plus 1 minus theta n divided by h and minus k theta n plus 1. So everything is known to you. Okay, so this is how you do the whole thing using the backward differentiating formula. And we also saw that this approach is a much more stable approach compared to your central differentiating approach. Is this clear?
Yes, ma'am.
Yeah. So now let us look at Newton-Raphson. Okay, in Newton-Raphson, when we try to solve, we always solve using the analytical method. Okay, so in Newton-Raphson, we need to find out what was Newton-Raphson used for. Newton-Raphson is used for if you have to solve a non-linear equation, basically. Linear equation also you can solve, but that is a much more easier problem. No, sorry, linear equation you can't solve. Newton-Raphson is for, just a second. Newton-Raphson, that is NR method, is for non-linear solutions. Okay, so that is if you have a function f of x, we need to find where this f of x is equal to 0. So here we have an equation 2 minus x plus ln x. So what do? We have to find the derivative of this formula. So just give me a second. Okay, so we used to do it like this. The x new value is equal to x minus f divided by df. Okay, so here what is df? df is the derivative. This is what we used to do, and we used to use analytical derivative. So here what we're trying to do is, instead of analytical derivative, let's try if we can make use of the numerical differentiation formulas that I have seen in this case. So let me go to the Matlab code, just give me a second. I hope you can see Matlab. So this is a function that we're trying to solve for. That is 2 minus x plus log x. Remember, log in Matlab gives natural logarithm. If we need logarithm to the base 10, then the function is log 10. Okay. So now for Newton-Raphson, you always need an initial guess, which you keep improving until a certain tolerance or some the error goes below the tolerance. So here we are starting with x0 is equal to 1.2. And my tolerance, that is my error tolerance. That is the difference between x new and x. This difference has to be below the tolerance. Okay, so the tolerance level is given as I1 e raised to minus 4. The maximum iteration, it could be 50. It could be any value. Here I've just given 50. Now what happens is I initialize x value to be the initial value 1.2. I start the loop. You can also do with a while loop. That is completely fine. So right now, let me run the loop from 1 to the maximum iteration. That is 1 to 50. Now this is my function. So my function, let me just show you the code. Oh, nr_fun, sorry, I was looking somewhere else. So this is the function that I already have. nr_fun is equal to as a function of x, and here this is the function that we have. So here this f will give me a function value at the point x. Now this is the analytical function value. Analytical function value is what? You have to take the derivative of this. So the derivative of d by dx of 2 minus x plus log x is nothing but 0 minus 1 plus 1 by x. That's exactly what is given here, minus 1 plus 1 by x. So this is an analytical derivative. Now what you do, the new x value is the old x value minus f divided by the analytical derivative or the derivative just. Now what is the error value? Error value is the absolute difference between the new x value and the old x value, like what I have said here. Okay, and then after calculating the error, you update the x value with the new x value. Okay, and this loop will continue until my error goes below the tolerance. When the error goes below this I raised to minus 4, then we break out of the loop. Okay, till then the loop will be running. So let me just run this for you using analytical derivatives. So using analytical derivative, we just got the answer within 5 iterations. So the first answer error is 5.899 and as we progress from iteration, it will be falling down to 2.333 e raised to minus 0.04. Okay, and the answer for the solution you are getting very close to 3.1462. Now, instead of using analytical derivative, let's look at the numerical derivative. So for numerical derivative, what are the formulas we have? We have central differencing, we have forward differencing, and we have backward differencing. And we have very clearly identified that central differencing is more accurate. So here, let us use central differencing formula. So for that, first you need to, what we are trying to do is we are trying to replace this. Okay, so let me just comment out this thing, this line. Next, what we are trying to do is I need a small step size for calculating the central differencing. That step size I'm taking it to be very small, i.e. minus 6. And then I calculate the derivative using central differencing. Central differencing, what will happen? The function value at x plus h, so that is taking one step forward, minus the function value at x minus h, that is taking one step backwards, divided by the total difference between the steps differences. So there is one step backwards, one step forward, so that will be 2h. So this will be my central differencing formula. Now what will happen, instead of this analytical derivative, in this equation, I'll apply this numerical derivative, that is x minus f divided by df. So let me run this code again. Now what you will see is, you will see the answers are very, very similar. Okay, so that is because in this particular case, in numerical derivative and analytical derivative are giving a very, very close match. Okay, that may not be always the case in all the functions, but here in this case, if you don't have access to analytical derivative, so basically where is it useful? In cases where you don't know how to, you don't want to calculate the analytical derivative. If you feel like it is very complicated to calculate the analytical derivative, you can calculate the function value at a forward point, you can calculate the function value at a backward point, and then you can calculate the numerical derivative. Okay, so if the numerical derivative guess is very, very good, calculation is very, very good, then what will happen is you will be getting the almost the right answer. So the answer for the answer for this question is 3.1462. Any doubts on this part?
No, ma'am.
Yeah. So let us move on to the next part. That is experimental data having noise. So this is, you have a rate of a reaction with respect to your temperature. So temperature T by T0 means T0 is a reference temperature. So here when T by T0 is equal to 0, 0.5, 15, etc. and calculating the rate of a particular reaction. This is ideally, so if you are experimentally calculating the rate of the reaction, what will happen is, so if you have an equation like this, just a second. So if you have an equation like this, dr by dt, that is rate of the equation, is given by some function. If you can utilize this function, you will be getting some ideal, if you're expecting ideal behavior, okay, you will have some equations defining the rate of the reaction. And if you're saying that, okay, my system is going to behave ideally, you will have this rates at the particular time intervals. But what if when you're trying to calculate the rate from an experimental setup, obviously there will be noise associated with it. So this is the rate of reaction from the experimental setup. As you can see, there is slight difference. So 1, 0 0.0, 0 0.99, 0 0.854, and there are some differences like that. So here in the plot, you can see the blue line corresponds to the ideal rate of the reaction. Okay, and the red dots corresponds to the experimental rate of reaction for the corresponding time. So here you can see in this starting, the match is very, very close. The blue and the red dot is almost very close. That is because 1 and 0.9 is very, very close. Okay, and now here we have 0.854 and 0.89. So this is like a error here. Okay, next point you have like a error on the other side. Okay, if you see this is in the positive side, this error is in the negative side. Again, you have an error in the negative side, again in the error in the negative side. You'll understand why I'm talking about the side of the errors, okay, later. So what we're trying to do is, let's try to find the numerical derivative. But the ideal thing is you have the ideal value. So from the ideal value, if you find the numerical derivative, you will get a set of values. And let us find the numerical derivative with respect to the experimental value. Okay, so numerical derivation, so numerical differentiation of noisy data, and we'll try to fit a curve. Okay, during the experimental data, let's try to fit a curve and then do the differentiation. Okay, when we do that, we might get a smoother slopes if our curve fitting is very, very good. So this is what we are trying to see. So yeah, just a second. This is a system that we are trying to fit using regression. I'll show you that. Clear? Okay, so here what we have is we have the time variable from 0 to 2.5 as given in the question, and this is the R ideal value and this is the R measured value. Okay, now what I do is the ideal value I'm plotting using a blue line and the measured value I'm plotting using red circles. So what happens is I'll be getting this curve. Just a second, there is a problem with my Matlab. Ideally, you'll be getting this curve. Okay, so where there is the same curve that we saw in the, okay, so here we have like a positive error, there is a negative error, negative error, negative error. Okay, so the signs of error I'll explain why I'm emphasizing on that. So let me again share Matlab. Okay, so now you have your ideal values and the measured values. Now it's just numerical differentiation if you are using the R measured and the R ideal. So let us see, we have to run for how many points do we have? We have points from 6 data points are there. Okay, 6 data points are there. I'm trying to find for the interior points, that is from point 2 to 5. Let me find the differentiation using central differencing formula. So that is why I run the loop from 2 to 5, and differentiation with respect to the measured value, that is with respect to the experimental value, will be Ri plus 1. Okay, so that is for my second data, second index, I'll be just taking the third index minus the first index divided by the temperature difference. Okay, so I hope you understand this central differencing formula now. Okay, that is R measured I plus 1 minus R measured I minus 1 divided by the temperature difference between these two. So this is from with respect to the experimental quantity. And this one R ideal is R ideal I plus 1 minus R ideal I minus 1 divided by the temperature difference between these two readings. So now if I print this out, this is how the values will look like. Now we can see with respect to the first point, your derivative is, okay. For this, I'll have to do one thing. Just a second. I think I should be running this section again. Why is this coming like this? You. Okay. I think this is much more better. So here what happens is, with respect to the first point, okay, with respect to the first point, you can see this is one was respect to which was the first one I printed? R measure. Okay. So the first column with respect to the experimental quantity, and the second is respect to the, okay. So this is experimental and this one is ideal. Okay. And here you can see for the first value. Okay. And the first value you can see at this point. Okay, R ideal. So basically what we're trying using differentiation is trying to find the slope. Okay, at this point that is correspond. If you're finding using R ideal, this is the slope. It will be in the blue line, right? This will be the slope when we're trying to find using the ideal value. But when we're trying to take the differentiation with respect to the experimental value, your one experimental value is here. And for this we are using this and this. Okay, if you join a line, you will see the slope is different, right? Let me just do one thing. Okay, you will see the slope is different. Okay, so this is why you will see a difference in slope here. That is -3.1 and -2.8, but both are along the same direction. So that is why you will be getting both minus minus. Okay, both are decreasing, but both are in a slightly different value. Now let us look at next data point, that is -0.36 and -262. That is corresponding to this. So your actual slope is like this based on your ideal value. But what you get using your data points will be based on this one and this one. So let us try to join a line here like this. So the slope is different, right? Now the slope is different like this. Okay, so that is why you can see the difference here. Now, if you look at the next value, this is like very closely matching 2.6 and 2.514. Why is that? Why is that? Because for this point, you are calculating the slope, real slope here. And for the so for the measured value also you can see this point is having a negative error. This point is also having a negative error. So if you join these 2 points, you are getting a line which is having almost the same slope as this one. Okay, so this is why I said, so if one point is having a negative error, other point is having a positive error, then your line will be more like, will not be matching to your real value. Okay, here the line will be like this. But here the line will be like this. Here this line and this line has the same slope, and this and this doesn't have the same slope. Okay, so this is why I said, so that is why, since the errors are towards the same direction, that is why you have like similar derivative values even though you are using the one with the noise. And regarding the last point also you will see a difference, because why will it that be? So here the actual derivative is like this, and the derivative with respect to the data points, that is this one and this one. Okay, let's join. You will see how different the slope is. Okay, so that is when you're trying to use the experimental value and comparing it to the ideal value. Now, instead of using this experimental value directly, let us use some curve fitting. So for the curve fitting, this is the model that I'm using. So this is the model. Let me just share Matlab. Yeah. So the function that I'm trying to fit is y is equal to a0 plus a1 t by t0 plus a2 t by t0 square. This t by t0 is my x-axis. Okay. So now what will happen is I need to fit a function like this where there are 3 unknowns a0, a1, a2. This method we have already seen. Okay, linear least squares method. So the first column will be all ones and the second column will be the coefficient. Okay, so here t by t0 values you have to take, and here, so basically let me just go backwards. Okay, so you already have t by t0 values here. Yeah. You already have t by t0 values here. What you do is we also create a column for t by t square. And for the first value, we use these two equations. For the first row, we use these two equations. So it will be what? 0, 0.25. This will be 1. Okay. And so on, you will have values. So this is what you will be using in the next slide. Okay. So this is 0. This is 1, 0, 0. And again, this column, it's all will be all ones. This is 0, this 0.5, this is square of 0.25. 1 square of 1, again 1. 1.5 square of 1.5, 2.25. 2 square is 4, 2.5 square is 6.25. You have got this matrix, you have got the unknown matrix, and y1, y2, y3. Again, you're trying to fit the experimental value. So it will be 0.99, 0.89, etc. Then what do you do? If you want to find the A0, A1, A2, you have to just invert it, and then you will be getting your x values, that is A0, A1, A2. Once you've got it, what will happen? You can try to fit the curve. So this is what we'll be trying to do using Matlab. So first let me create the x matrix, that is ones, t and t square. Y is nothing but my r measured value. My phi value is inverse of y multiplied by x, or x bar y. Sorry, inverse of x multiplied by y. Okay. So my phi value is a1 is phi 2, a2 is phi 3. Okay. Now this is the function that I have. Just a second. Let me do the curve fitting and see the values. Just a second. Yeah. So now the function that we tried to fit is this. Okay, the function that I tried to fit is a0, a1 t by t0 plus a2 t by t0 square. Now I need to take the differential of this function. So that is d by dt. Okay, it will be equal to a0 as a constant. So it will be going a1 will be there, and t by t0, the square, this 2 will come here. So a1 plus 2a2 t by t0. This is my derivative. Okay, this is my derivative. So let me take this. So I'm manually calculating the derivative here, a1 plus 2a2 ti. That is my derivative that I calculate using fitting. Now what I do is I use this one and compare it to the derivative that I'm getting using the numerical differentiation. So this is regression derivative, and this is my numerical fitting with respect to the ideal value. And let me compare this. I'll run the whole code. Okay. So this you'll see with respect to numerical derivation, you will have differences here. The first point is different. Here also the first point is different. With second point also 3600. Now this one is a close match. When you try to fit using regression, we got a close match to the actual case. Here again, you have a close match in both the cases. And compared to the next 0.16, this is anyway a better guess than your directly using your experimental data. So this has been already done in your chemical experiments. When you have experimental data, we try to fit a curve so that you get slopes and everything better. Okay. So did you understand what we are trying to do in this session? Any questions?
Ma'am,
Yeah.
ma'am, can you explain it again from this of regression part, ma'am?
So what we did is, if our ideal value is so scattered, our ideal value is so scattered like this. In this, I know the scattering is not too much, but if you're using this scattered value, what will happen is the slopes that you're getting will be very uneven. Okay, because your scattered value, the slopes will be calculated based on these two faraway points. Just a second. Okay, so for this point, we are using these 2 points, which are faraway points, right? But on the other hand, if you're trying to fit using regression, what will happen is you will have a function like this. So So regression, if you're trying to do, what will happen is you will have a line, a smooth line like this. I know it didn't pass through all the points, but it should be ideally passing through all the points, okay? Just a second. Okay, you'll be getting a regression fit something like this. Now what will happen is if you find the gradient at a different point, at this point, if you want to find the gradient, your slope will be this. Okay, it's like a local slope. It'll be like a local slope. Okay, in most of the cases, this local slope is very much better than taking a two endpoints. Okay, another thing is that here you can see, that when you're calculating derivative, there is a denominator h. How smaller the h is, you're gonna get a better derivative, right? So when you take this case and when you take the regression readings, you can see how far these values are. Okay, but on the other hand, if you're using this analytical derivative, that for analytical derivative, you need a function. Okay, only then you can do dy by dx. So this function, we find it using regression. And then you take the analytical derivative. So then what happens, analytical derivatives will give you the local slopes better than taking values from this far away. Understood?
Yes, ma'am.
Yeah. Let me go to the next part. So this is PDEs in multiple variables. We have already solved PDE problems. Just that what happens if you have like multiple, we have solved for a single equation. Okay. So this is what I showed, the method of lines already I had explained. Now here we have like three variables to solve for. That is CA, CB and CC. In that case, how do we solve it? So we are given a transient equation. So here there is a reactor. Imagine there is a reactor. The reaction that is happening is you add A and B to the reactor and it will react and give you C. So A plus B giving C. This is a reaction that we are looking at. So when the experiment starts, you are starting CAN. Inlet CA concentration is 1.2. Inlet CB concentration is 1. You don't have C because C is the product. Okay, so only once the reaction starts, you will be getting C. So CB IN is actually 0. Initially CB IN is equal to 0. Now what happens is you have to say that as I progress across the reactor and also as my time progresses, I need to find what is my CA, CB, CN at all the grid points. Okay, and also change with respect to time. So this is what I'm intending to find out. So with one variable, you know how to do it. If you only had this equation, so if you only had, just a second. So if you only had this equation, how do you do? Okay, we write dCA by dt. You use central differencing. So you take it to this side, whole thing to this side, equal to minus u. You write dCA comma I minus dCA comma I minus 1. Okay, this is if I'm using backward differencing. Okay, if it is central differencing, it will be I plus 1. Okay, and divided by 2 h if I'm using central differencing minus k CAI CBI. Okay, then I'll have a set of concentrations like CA1, CA2 up to CAN plus 1. In this one I know I have to only solve for 2 to n plus 1. Okay, this is what we used to do when we had a single variable. Now what we do is the same equation, you write CB dt. Okay, then you will have here also 2 to n plus 1 data to solve. Again, you write it for dCC by dBT. Also, you will have a set of equations to solve from 2 to n plus 1. Okay, so 2 to n plus 1 means this has n equations, this has n equations, this has n equations. Now totally you will have 3n equations to solve for. That's the only difference. Okay, we have to properly write this like properly order the CA, CB, CC in such a way that okay, it can be easily solved. And how many equations you will have? You will have 3n equations. One set of n equations for A, one set of n equations for B, another set of n equations for C. Okay, and you have to combine it in such a way that you get you can solve for the system. So how do we combine it? Just a second. Yeah, this is how you combine it using method of lines. Okay, remember you have n plus 1 grid points, right? So for n plus 1 grid points, we are not looking at the CA, CB, CC at 1. Okay, that is CA, CB, CC at first grid point. We already know that is given to you in the question. I'm not trying to do that again. So CA, CB, CC at the second grid point, CA, CB, CC at the third grid point, and CA, CB, CC till the n plus 1 grid point. So this is what I'm trying to do. Okay, now we'll have to code it in such a way that you have to group it this way. That is first grid point, second grid point till the n plus 1 grid point. And this is the difference for CA, CB, and CC also will follow the same equation using backward differencing. Okay, I hope this part is clear.
Yes, ma'am. Ma'am, these equations are called coupled PDF.
Yeah.
Ma'am,
Why?
I have one question. Can you explain that how to write the code? I don't know whether I can ask this question in this session.
How to write the code in the sense, okay,
Like
first,
I have a coupled PDE,
uh,
which is my research based.
uh,
So if I display, can you explain the basic part, how to write the code, ma'am, for any of the method,
so
like
for
shooting method or with the Rangekuta method by using that? Can you explain, ma'am?
so
Actually, if you say, I
you're
will.
talking about you have a PDE, right? Okay, show me the problem.
Okay, ma'am. I'll display. I'll take some time, I think. Hello, ma'am. Hello.
Yeah, I
Ma'am,
think.
I've just posted that image of the coupled PD, equation number 8, 9, 10. I put it in the chat box, ma'am. Can you see that?
Yeah, I saw it in the chat box. So this is a third order PDE, right?
Yes, ma'am.
What are your independent variables? What is f of 0 is equal to 0? What is that 0 in that?
Ma'am, it is an initial condition, no? F of 0 is equal to 0.
It's like the length of
Count.
something like that? Okay. So there are like three things that is changing, no?
Yes, ma'am.
third
F,
order.
theta, and phi. So,
So this will be a bit complicated, but one thing I'll tell you to start is, like, if you're going with whatever has been taught here, just a second, where is my oh. Yeah. So right now what you can do is you have here F, okay. I'll just go with one equation, okay? F triple dash. So
okay,
F
ma'am.
triple dash is basically d by d cube by dx cube of F. Okay.
Hmm.
This thing, how we used to solve the second order is we have to convert that into two first order PDEs. This thing you can convert this into, let me say that d square F by dx cube is equal to y. Sorry, dx square is equal to y. So then what will happen? df by dx cube is equal to dy by dx. Oh, this is just a second. This third order is a bit complicated.
Then it will be only two equations, no, ma'am.
Yeah, dy by dx. That will be d
Here
square
also you have
by
taken D.
dx square.
Okay.
Okay, it will be d square by dx square. Then what happens? So, okay, then you'll have to take one more variable. That is d.
D, some other variable we
Yeah,
can take.
dy
Like
by
du
dx,
by.
let you assume, for example, what would I do? I'm just taking k, okay, for time being. So then d square y by dx square will be equal to dk by dx.
Okay.
Okay, so now how many first order equations do you have? So this is equal to some function g, as per your question, some function g. Okay, this is your starting point. So now you will have so let me do this thing. D square y by dx square is dy by dx. And there are initial conditions also given to you, know. F dash is given. So yeah, like this you can split. So but how many equations will be there? That's what I'm looking at. Yeah. This is equal to dq by dx square. Now how do we solve it? We'll have to form a vector. So the vector is dx cube by so it should be I'm just writing here. Now this is split into two. So this will be dy by dx and this will be dk by dx.
dk by dx.
And you will have what else?
And k, ma'am. First one.
And k,
dy
right?
by.
Yeah, it will be k only, no?
First.
Okay, it's confusing. You could be able to split it up anyways. That's what I'm trying to do. Just a second. Here in this case, we'll have y, which is nothing but dt by dx is equal to y, and dy by dx will be equal to your equation, that is g. Okay, if you're assuming this is g, so then your variables will be t and y.
Then we have written this vector wrong, ma'am. Then dk by dx, again k, again y. So here
Yeah.
yeah.
So it will be, so here you will have y, and lower is anyways y, and top, top it will be f, right?
Last one is dy by dx. The second term should be dk by dx, and the first term should what we
F,
can
right?
write df.
That's what I'm thinking. No, this is okay. This is okay. The first one, what will it be? I'll see how to solve this. Triple derivatives, even I haven't tried.
Okay, ma'am. It's okay, ma'am. You can
I'll
continue.
see. Okay.
Mm.
Okay. Just can you do one thing? So this is my mail ID. Just send this to my mail ID. Okay.
Where is ma'am? Where is
I'm
your?
sending it in the chat.
Okay.
Okay.
Yes, ma'am. Thank you. Thank you for giving mail ID, ma'am.
Yeah. So we have to group this one. Okay. So we'll try to do that. So what we do is we say the length of the road is 1. I'm dividing it into 50 interval with respect to position. Each of my interval will be after the span will be L divided by N. Now what happens? I told you there are 3 n equations that I have to solve for. So how many equations? Variables are there? 3 n variables are there. So I declare all zeros. 3 multiplied by n, all zeros will be there. T-span is I'm only intending to look at time interval 0, 0 0.5, 1, 2, and 5. So there is only 5 reading with respect to T-span. Now I have an ODE solver. It will solve for the y variables. This is the function that will be having all the ODEs. I'll come to that. Okay. Now T-span is from 0 to 5 with this time intervals, and y0 is your initial guess for the y. Remember that we only have 3 n unknowns. Now what happens is this is your ODE, the function that is writing the ODEs. So this is y. It will take all the 3 n variables. These are the constants that is given to in the question. That is u is equal to 0.5, k is equal to 1, cn is equal to 1.2 bar 1.2, 1 and 0. So this is just a second. Okay, this is CA, this is CB, this is CC at 0. Okay. Now what happens is the total length is 1. And now what I do is I have to calculate the intervals. So from here, the size is 3n. So if I have to calculate the interval number, I have to just divide by the 3. That is 3n divided by 3. I'll get the n number of intervals. H is nothing but the space, that is L divided by n. Now what I do is, remember in my CA, in my y vector, basically my CA, CB, CC were interconnect. Like it was mixed. CA, CB, CC of first one, and last one is A, CB, CC of n plus 1. So these are mixed. So what happens is from that y you have to extract CA part, you have to extract CB part, and you have to extract CC part. Okay, the y in the y vector everything is jumbled because it is arranged with respect to your grid points, the position grid points. Now what will happen is we'll do this from y. CAs are starting from the first index, you jump by 3 steps till the last. So what happens? From this, if you jump by 3 steps, what will happen? You will end up in the next set. You will get the next CA. Again, if you keep jumping, okay, so this, if you imagine this is the next set, again, if you keep jumping here, there will be another CA. Okay, so you keep jumping by a step size of 3. You starting from the first index, you will be getting the CAs. If you start from the second index, and if you jump by 3 steps, you will be getting CB's index. And if you start from the third index, and if you keep jumping by 3, you will be getting the CC index. Now, this will only have 2 to n plus 1. We need the whole vector. So, for that, you will add the first reading also. This is the first initial point CE, initial point CB, initial point CC. And that you add to, so this will have 1, this will have 2 to n plus 1. Okay, now let us move downwards. So here we have CA, DCB, DCC, n plus 1 equations are there. I am declaring all to be zeros. And remember, in the loop, I am only intended to solve 2 to n plus 1. I equal to 1, I already know. So all this equation has a common term, that is K, CA, CB. Okay, this was a common term in all the equations. So this I am calling R. So first let me calculate R. R is nothing but at a particular index, it is CA multiplied by CB. Now this is my equation for CA. So that is U. This is a backward differential formula, CAI minus CAI minus 1 divided by H minus U minus R. This is for B and this is for C. Okay, remember here. Yeah, remember here both it is minus R and here it is plus R. Okay, like what is given in the question. Now what happens is I have to send it back to the solver. But remember, while sending it back to the solver, the order has to be again rearranged. I can't just group CAs and CBs and CCs together and give. It has to be CA, CB, CC, again CA, CB, CC and so on. So for that, what I do, I again run a loop 2 to n plus 1. Then in dy, I first create a vector like this and I concatenate. So dy is initially null null vector. So then null vector. Then I take the first indexes of all this A, B and C. I group them together and to that I concatenate the second indexes of CA, CB, CC. And again I group the third index and so on. So finally I'll be getting this order. Once I get this order, I'll be sending this as the output. dy is the output here. Okay, dy is the output here. So that is what will be given by the multi-var PFR file. Okay, so now let me run this code. T-sol, you can see it is for 0, 0.5, 1, 2, 5. Let us look at how Y-sol looks like. From here only you can see Y-sol is having 5 rows and 150 columns. Okay, so 150 columns is 5, 150 columns is, so we have taken 50 data points. So 50 into 3, that is 150 values we are trying to solve. Okay, so this is 150 values. And what is 5 rows? This row number. Okay, so this is basically 5 and 150 columns. This is corresponding to time. And this one corresponds to CA, CB, CC at grid point 2, and CA, CB, CC at grid point 3. CA together it will go CA, CB, CC at grid point n plus 1. Okay, likewise it will go. So let us see the Y-sol ones. See? This is how it looks like. Each corresponds to, this corresponds to first time, that is t equal to 0. It was given that everything is 0. So t equal to 0, everything is 0. T equal to starting, you have the values that is given to you. Okay, now let's try to plot this. So the plotting function is, it's already given here. So just like we extracted here, okay, just like you remember from y you extracted values like this part. Just like this, we'll extract again values back from your y solve. So this is your first, at the first index, what is the value? Rest of the index, what do you do from y solve? You start from the first, uh, so this is a time, okay, this is just a time. X values, y values you do 1 with a step size of 3 towards the end. For C also, this is your starting value. Then what do you do? This is your time, and this will be 2 to end with a step size of 3, and the next will be third index to end with a step size of 3. Okay, so this will give you all CAs. Okay, and I time means it will give you corresponding to specific time. Okay, so you're telling which row number and which all columns to extract to get CA. This will tell you which row number, that is with what time you want, and give the corresponding CBs. So now what I'm trying to plot is, I am plotting with respect to position CAs only. I'll be getting 5 lines. Each of the line corresponds to each time. First corresponds to T0, T0.5, T1, T equal to 2, and T equal to 5. So this is how the figure looks like. Okay, this is the change in the A concentration. At T equal to 0, you can see how the concentration is. Okay, at T equal to 0.5, you'll see this decreasing. Again, T equal to 1, T equal to 2 is the violet one, and T equal to 5. The most common thing that you can see is, you can see the concentration of A is decreasing. Why is it that? Because you have a reaction, A plus B is equal to C. So as the reaction progresses, you will have the amount of A decreasing because it is slowly getting converting into C. Now the same thing, if you plot for, let me comment this off, and I'll plot for B. What will happen to B is, it's again the same behavior. Because why? Again, B is converting into C. So what will happen? Initially, B will have a good concentration. It is equal to 1. And as the reaction progresses, your B is slowly getting converted into C. So you will have this drop in concentration. Now let us look at C. So here you can see the concentration of C is increasing. Okay, the concentration of C keeps on increasing. At T equal to 5, we can see there is a sharp increase. So you can see here that the concentration is dropping. That is because your system has not reached steady state. Once your system has reached steady state, there will be a sharp increase in C concentration. So that is why you can see at T equal to 5, your system has, you can see there is a sharp increase in C uniformly. Okay, so did you understand this? Any questions?
No, ma'am.
Yeah. So now what we'll try to do is, we'll try to solve some problems as we used to do before. Okay. Apart from this session, we'll also have one extra summary session where I'll try to include questions from all the topics that we covered. So that will be like a practice session for your for your exams, and it will be also a quick recap of whatever we learned. Okay. I'll do that on Monday. Right now, just as we used to do before, let's try to do this problems. I'll give you a few minutes and then we'll discuss. Okay. So this is Newton-Raphson plus numerical differentiation. Analytical derivative is given. So analytical derivative is given to you, but what I want you to do is, you have to try to using the numerical differentiation. Okay. And if you want, you can also compare it with the results with the ones which you get using analytical derivatives. So this is what I need to do. I need to report the value after the first iteration. I need to report the error. I have to repeat that for the third and the fourth iteration. So run it for some 5 iterations or something. And at every iteration, you need to report what is the t value and what is the error value associated with it. Okay. So I'll give you some time and then we'll discuss the answer.
Ma'am,
Yes.
ma'am, assignment 11, no. Second question, I did not understand how to do it.
Is the solution given to you?
No, ma'am, not yet.
Oh, I think the deadline.
Deadline they've given on Monday.
Oh, I can't. Okay, maybe. Let me just see. Okay. Just give me a minute. What was the question number?
Ma'am, problem 2.
Oh, okay. See, in this thing, no, I don't know how to share. Can you see?
Yes,
Yeah.
ma'am. Yeah.
So they are telling, I think the numbering they meant it is from y0 to yn. Okay, yn is the last node. I know we should usually be number from 1 to n plus 1. So here from the understanding that I understand is yn is the last node. So if you're applying central difference formula, you will require yn plus 1. Okay, so that is like a ghost node because we don't have that node in our thing. So if you're writing the equation for the last last node like this, that is just a second. That is dy y dt at nth node will be equal to this alpha beta. I'm not looking at the equation right now. Okay, alpha using the for back central differencing, it will be yn plus 1 minus 2 yn plus yn minus 1, right, divided by h square minus alpha, then this minus beta, the function part. Okay, so here what happens is when you write this equation, you don't have this yn plus 1. That is the whole point. So for that, what you do is we have to substitute this equation, that is cyn plus 1 plus c2.
This assignment we felt very difficult, ma'am. Assignment 11.
Yeah. What is the value of C1 and C2 is the first question. Yeah.
That also I did not understand here. How to find out C1, C2 and all.
I can't tell the whole thing because it's not the deadline is still there. But central differencing formula, what is the equation? Central differencing formula is, so this is yn minus 1, right? Yeah, so if you write this yn minus 1 minus 2yn a2 is 0. Okay, I also need some time to think over this question. By the time you can look at the question, okay, I'll also see. You can look at the question that I've shared, okay?
Okay, ma'am.
Just give me a second. Oh, okay. Okay, I was on mute. Okay, fine. So the thing is, see, I'll just repeat it again. Remember, so here I'm given this condition, okay? That is dy by dz is given to me at x is equal to 1. That is equal to minus 0.5. Let me write this with respect to the central difference formula. That is, what will be? My last node, I'm calling it as yn. So it will be yn plus 1 minus yn minus 1 divided by 2h is equal to 0.5. Okay. Now, do you see this equation? Yn plus 1 is equal to Cyn minus 1 plus C2. You see the similarity between these two equations? So what you have to do is rearrange this equation into this format and you compare the coefficients. You will be getting C1 and C2. Okay?
Got it now.
Yeah. So once you have C1 and C2, then the things are easy because in the loop, you have to write the last equation, right? The last equation that is you have to write for this. That is dy by dt is equal to alpha times central differencing formula you have to apply for. That will be yn minus 1 times 2yn plus 2yn plus 1. And you will have h square. So here this n plus 1 you don't know. Then what do? You can put this equation. Don't write this. Instead of that, you put C1 yn minus 1 plus C2. Now all the things are known to you. C1 is known to you, C2 is known to you from the first part. Just that the last equation will be of a different format. So this, you can add it up. Okay? Yeah. Did anybody solve the question that we were sharing?
Solving, ma'am.
Yeah. I'll give you 2-3 minutes more and then we'll discuss the answer. So let's discuss the answer. Sorry. Okay. So this is a function that we're trying to solve for. 4 log 1 divided by 1 minus 0.02t minus 0.04t minus I, or t minus 1. So the initial conditions, I'm just using t0 is equal to 10 and maximum iteration, I'm only using 5 because in the question they have only asked for 5 iterations. So I run it using max iter. This is my function value. So if I'm using the analytical function, this will be my function. Okay, so first let me do one thing. We'll try using numerical derivative and then we'll compare with the analytical derivative answers. Okay. So for numerical derivative, I declare h to be a very small value. Then I calculate the numerical derivative using central differencing divided by 2h. And this is my Newton-Raphson formula, T minus F divided by dF. So this is my new update. I calculate the error, the absolute difference between the old T and the new T, and then I update the T value. Now what happens is I am displaying what all things. So it's this particular iteration. My T value I'm displaying it as here, and my error value I'm displaying here. Okay. I'm also adding this T and error value into an array so that it's easy for my comparison. So let me just run this code. This is if I'm using numerical derivative. Let me see what will happen if I'm using analytical derivative. Also, I'll just comment this out, uncomment this, and comment this. I'll run it again. Okay, so actually you can see it's a very good match. The central differencing numerical derivative, it's a very good match to your analytical derivative. So that is why you're getting this exact values. Okay, so did you understand this part? So should I explain any of this again?
No, ma'am.
Okay.
Understood that.
So let me move on to the next question. So this is a recap of what we did earlier, the fitting the model. So nonlinear fitting, you can use method of least squares, also use LSQ nonlinear, okay, and find derivative at each point using the numerical derivative. So it's up to you, okay. Compare the derivative to the measured data using the measured data and the fitted data. Okay, just like we did regression and then we did numerical derivative, right? One of the examples that we saw in today's class. So here also the regression, this is the model you have to fit. How you want to fit it, either using LSQ nonlinear or method of least square, that is your choice. But you have to fit the data and then take the derivative. Okay, and that is how you have to do it. I'll give you a few minutes and then we'll discuss. Because of time constraints, let's try to solve this. Okay, so if I am using method of least squares, you know how to do this. So first I have to convert this into a linear problem. So what I do is I take a reciprocal, so I'll get a function like this. So now the formula, it will be in a form y0 is equal to a0 plus a1x, where y is nothing but 1 by r, a0 is b by a, and a1 is 1 by a, and x is nothing but the directly your time variable itself. Then you can solve it using linear regression, or else directly pass on this function to LSQ nonlinear and it will solve the nonlinear regression part. So this method of least squares, this equation how to do it, and then the phi can be taken as x transpose x whole inverse x transpose y. Okay, this is method of least squares, and if you are using LSQ nonlinear, this is the syntax. You will have to give your function which will give you the errors, that is your model minus the error that is given to you. So this has to be yi minus yi is the actual value, and this is what the model gives you. And then P0 is the initial guess of your parameters. And so LSQ nonlinear minimizes the square of these errors. Okay, so this is what we used to do. So let us try to do that in Matlab. So you see, this is the R value and the T value. Right now I'm using linear least square method. So this is my linear transformation, and this is how I calculate my phi value. Remember, the phi value also I have to extract the actual A and B from the phi values. So this is 1 divided by the phi 2, and this is the, so this is so the phi 1 has to be multiplied by A to get my B. So these things we have already done it in our previous weeks. Okay. So if you're using LSQ nonlinear, this is what I have to do. I have to give an initial guess. This is my LSQ nonlinear. This is my function. Just a second. Yeah, this is my function here. You can see the R value. This is the model, and this is the error. Okay, R minus whatever I get from the model. This is taken as the output here. Now going back. So let me see if the phi value is same for both. A, B. 10.2690 and 27.39. Using this, let me see, running this section. Okay, I'm getting a slightly different A value. A value is 9.5409 and B value is 23 point. Okay, it's your wish, like it's not specified in the question, so you can go with any of them. So right now what will happen is when I'm running this code, this A value will be overwritten. Okay, A value will be overwritten with the solution that I get from LSQ nonlinear. Okay, now so I'll run this section by section. One section, LSQ nonlinear section. This is how my regression fit will look like. Okay, so what am I plotting here? I am plotting the t-solve and corresponding fitted function from this function that is given to me. Okay, that is why I get a slope like this. But my actual data is scattered, but this is the fitted function that I get. Now I used to use numerical derivative. Numerical derivative, if I'm using actual function, this is this from, I'm only using for interior points. Okay, using central differencing formula. And this is using the fitted data. So for the fitted data, what I do, I take, so it's up to you. So this one only has 4 in the interior points, but for the fitted data have like higher points also. Okay, so I am taking for all the interior points. And let me run this. Mm. Oh, okay. See, my function value here, I took it for 10. So the t-solve is basically 10, 11, 12. Then I'll have 20. Like that, I'll go till 50. I only intend to find values at 10, 20, 30, 40. Okay, 50. So that is why in my loop, this is from 20. 20 plus 10 is 30. 30 plus 10 is 40. Only till 40 it will go. Just like this. Okay, I'm only finding for the interior points 20, 30, 40. So here you can see if I'm using numerical differentiation directly from the data, this is the derivatives that I'm getting. But if I'm using the fitted data, you can see this third point, it is like a mismatch. Why? Let us see how yes, you can see the third point. If the slope was there, the slope would have been like this. A straight line that is going from here to here. That slope is very much different from the slope of the blue line. So that is why you can see this discrepancy here, especially in the second value. That is corresponding to this data point. And the rest of them are a very close match. Okay, I hope you have understood this question. So let me move on to the next question. Okay, so this question you have to solve using method of lines. Boundary conditions are given to you. At x is equal to 0, one condition is given, and x is equal to 1, another condition is given to you. Initial condition with respect to time at t equal to 0, all c's are 0. So basically you need to solve for 2 to n. I equal to 1, you know the value, that is this. I equal to n plus 1 also, you know the value, that is this. You need to solve for 2 to n plus 1 using method of lines. Okay, and what all things you have to report? You have to report the value at t equal to 2, at z equal to 0.2, 0.4, 0.6, and 0.8. So basically, you have to take z equal to 0 to 0.8 with a step size of 0.2 each. And we have to do from time equal to 0 to 2. Okay, I hope these things are known. So now I'll show the question. I'll give you 2 minutes, 2-3 minutes, and then we'll discuss. Okay. So let's look at the solution for this problem. So first you have all the, okay. So this is for running. So first I'm dividing into 10 intervals. This is my initial condition that is given. Okay. So I'm just creating my first vector of C0. And I am only, that t-span is, as I said, the question has asked me to find a t equal to 2. So the t-span I'm just keeping 0 to 2. And y0 is I'm only solving for 2 to n, because first one I know, n plus 1 I also know, because boundary conditions are given. So 2 to n. So I use the ODE solver. I have this problem, I'll show this. Now the t-span is there, initial guess is there. Now this is the ODE problem. I'm giving all the constants that is there. Now I have the length. How many points will be there in y? There are total n plus 1 point, out of which 2 are not there. So n minus 1. So if I have to get the total length, it will be n minus 1 plus 1, that is n. Then I'm taking initial value to be 1. 2 to n comes from this y, and n plus 1 is 0. These two are the boundary conditions given to me in the question. H is nothing but L divided by N. First, I declare all dc dt to be zeros. Then I run the loop from 2 to N. Okay, because 1 and N plus 1 is already there with me. That is given by the central differencing formula here. And what do I extract out of dc dt? dc dt has n plus 1 equations, out of which only 2 to n, that is what I require to like give us an output. So this goes here, and I'll solve the ODE solver. Okay, you can see t sol has 65 and y sol has 65 is there, plus, so each row corresponds to each time and each column corresponds to your grids. Okay, so there are 10 points, so that is 10 plus 1, 11, 11 data points are there, out of the 2 are not there, so 11 minus 2, 9. So this is corresponding to C2, C3, C4 till C9. Okay. Now let us see how to plot this. So t sol and y sol, when I plot, I'll be getting time on my x-axis, y sol as in my y-axis, but I'll be getting different lines. Each line corresponds to a specific z value. So let me just, this will be the plot I'll be getting. Okay, each line corresponds to a specific z value. So the first line will be for z equal to 0.2, and next for z equal to 0.4, 0.6 and 0.8. Now, as per the question, if I want to extend, get values for x is equal to 0.2, you have to look at the y sol. The y sol, as I said, let me also look at the, just a second. Yeah, so since you're dividing into 10 intervals, every step size will be 0.1. So this is for 0.1, this is for 0.2. You start from 0, right? 0, 0.1, this is for 0.2. So that is in y sol, you have to look at the end if you have to get to the t equal to 2. And 2 reading means this is for 0.2. If you look at, this is 0.3 column, this is 0.4 column. So for 0.4, you take the fourth column. Correspondingly for 0.6, you have to take the sixth column, and correspondingly for 0.8, you have to take the eighth column. Okay, so this is how you display. I hope you don't have any questions. Is it clear? Okay. Then let's move on to the last question then. This is again using method of lines. I'll just give you 1 minute because it's similar to what we have seen last week also, and then we'll discuss. So let's discuss this. Again, at initial condition is given to you. Initial condition with respect to the position is also given to you. So you need to solve for 2 to n plus 1. And the domain has to be split to 50 intervals. Okay. And then they have asked us to find till t equal to 5. And this is the grid point 0 0.2, 0 0.4 up to 0 0.8. So let's look at the code. So first length is 1. We are discretizing into 50. H is equal to 1 divided by 50. And this is your position grid points. So first I have n plus 1 data points, out of which my first data point I know. So I only have n solutions. So 0, n zeros I have. T-span is from 0 to 5 because in the question they have asked me to find out for t equal to 5. This is my ODE solver. This is my ODE fun. T-span, I give the initial values. Now, this is the plotting part. I'll come to that later. Now, ODE fun, I'm giving all the constants. Okay. And n will be the length of C itself. Okay. Now, I have the full vector of C that will have the initial value and whatever I get from the function. Now, the D concentration, I'm declaring it to be n plus 1 zeros, out of which 2 to n plus 1. That is from the second node point to the last node point, I calculate using the backward difference. Or else you can do mix of central differencing and backward differencing. Here I'm using backward differencing because it is more stable. Then as an output, I extract from 2 to n of D concentration. That goes here. Okay. Now plotting, I'm plotting with the position and the y-sol. Okay, so let me run this. So when I plot the position and y-sol, you remember, just a second. Let me just look at the y-sol. This is the t-sol. T-sol, you can see there are how many data points here? How many data points I have? Let me look at here. T-sol has 141. So when I plot positions versus the y-sol, I'll be getting 141 separate lines. That is why you see this complicated lines, but you can see how the behavior is. Okay. Now you can look at y-sol. So 141 versus 141 by 50 is the thing. So every row corresponds to one time, one particular time, and 50 is for the 50 grid points that you divided here. Okay, is this clear? Any doubts? Okay, so that will be the end of today's session. Yeah. So thank you so much for attending and thank you so much for taking up this course also. I hope you have really benefited from this. And there will be a summary session also for solving more problems. I'll discuss that on Monday. You'll be getting a link and the reminder message and everything. Okay. So it'll be the same time, Monday 6 to 8. That's what I've asked for. Hopefully it will be on the same time. So thank you so much all for attending these classes, and I really hope the very best for you all of you and all the best for your exams. Okay.
Thank you, ma'am.
Yeah. So I'll be ending the session now, and the recordings will be shared to you. And also remember, one of you have sent me a mail. Okay, I'll look into it and I'll reply personally to you. Okay. So yes, thank you so much. I'll be ending the session now.